Imagine a plane of charge. This would be an extremely thin surface which has a uniform charge on it. And we'd like to know what the field is like in the space around this plane of charge. Alright, so first I'll pick a point that is located away from the plane. I'll call it P. And I want to see what field would be created by the point charges in the plane. Now we already know that a single point charge would contribute a field equal to E equals kq over r squared, where r is the distance from the point to the plane. But now that we have other charges in the plane, they're all going to contribute to the overall field at point P as well. So the one above will contribute a downward pointing electric field. The one below will contribute an upward pointing electric field. The one to the left will contribute a field that points to the right, and this one will contribute to the overall field as well. What's going to happen is the vector components that aren't perpendicular to the plane are going to cancel with each other. We're going to be left with a single electric field, which I'll call E due to the plane of charge. And we want to find a formula for it. So one way to do this is to create a Gaussian surface, which has one of its surface boundaries at point P. So the best type of shape to make here will actually be a cylinder. And we want that cylinder to be perpendicular to the plane. And we want it to cut through the plane. We want it to cut all the way through our plane and have it come out on the other side. So that it has two caps. There will be a flux through the front. And a flux through the back surface as well. We can also discuss the possibility of an electric flux through the side of our Gaussian cylinder. But let's make it clear that here we're talking about a very large plane. So large that it's going to be treated as if it were infinite. And if we're talking about an infinite plane, then it goes on in all directions forever. And the situation we see here with this positive charge, where it's got positives above and positives below and positives to the left, positives to the right, that would occur for every single positive charge, no matter where it was located in the plane. And so, at the cap of our cylinder, we're going to always find that the electric field is perpendicular to the plane. With that in mind, the flux through the side will actually be zero, because none of our field vectors point at any angle other than perpendicular to the plane. This means that the flux is totally dependent on the front cap and the back cap of the cylinder. So let's use Gauss's law for this. I'll replace the electric flux with this. Now, by symmetry, the flux through the front is going to be the same as the flux through the back. And we'll find that the area of the front is given by pi times big R squared, where big R is going to be the radius of our Gaussian sphere. Not to be confused with little r. Little r is the distance from the plane to our cylinder cap. Alright, so the area of the back will also be the same. Pi r squared. The field that comes out of the back is E due to the plane of charge. Alright, so we'll have E times A plus E times A equals Q enclosed over epsilon naught. Combine these two things into 2EA equals the charge enclosed over epsilon naught. Now, we're dealing with a surface, and we want it to be infinitely thin. Very, very thin. With this in mind, we can use the idea of area charge density being the total charge divided by the area of the surface. If we solve this equation, we'll get that the charge enclosed by our cylinder will equal the area charge density times the cross-sectional area of that cylinder. Now we can take our result that we got and we can plug it in here. We'll get 2 times the electric field of a plane times the area of the cap of the cylinder equals sigma times the area of the cap of the cylinder over epsilon naught. And the area here will clearly cancel. So no matter what size our cylinder is, that won't matter when it comes to evaluating the field strength at the location P. I'll solve for E plane. And we get that. This is an interesting and perhaps hard to understand result. What the formula says is that the field due to the plane doesn't depend on the distance that point P is from the plane. The field strength will be the same regardless. It only depends on the charge density of the plane. That's how many coulombs are on a square meter, for example. And it depends on the permittivity constant. That's it. It's hard to believe, but what it tells us is that if we are located here next to this charged plane, or here, we will feel the same field in both locations. That goes against common sense, because common sense would tell us that the closer we get to the charges, the stronger the field should be. At least that's how it was with point charges, and that's even how it was with lines of charge. But now, when we're dealing with a plane of charge, charges above, charges below, charges to the left, and charges to the right, apparently it doesn't matter how close we're standing to that plane. We're going to feel the same field regardless. And this gives us some mathematical proof for what we had claimed in the past, that when we're standing inside a capacitor, that's a region between two planes of charge, the field between those planes is constant. Using Gauss's law, we proved that the field next to a charged plane truly is constant. But interestingly, our analysis on the left was only really for one plane. So what if we do have two planes next to each other? Take a point between them, point P. Is there a formula that would give us the strength of the field inside a capacitor? E capacitor? Well, we have a formula for the electric field due to one plane. So could we use superposition then to find the electric field inside a capacitor? At point P, there would be a field due to the positive plate. This would push positive charges away from itself. But we're also going to feel a field due to the negative plate now. The negative plate would pull positive charges toward itself. So we have two contributions to the field. There will be a field due to the positive plate and a field due to the negative plate. We want to add those two fields together as vectors. Over here, I just have the magnitude of the field due to the plane. Now we can write our result in a different way as well. We can write it as a vector. N hat is a normal unit vector which points away from the plate. So whether we're going to the right or the left of our plate, the electric field should be directed away from the plate. That's what that says. So this is a picture of the n hat vector. Okay. So if we want to find our capacitor field as a vector, we should add the two fields together. I'll let to the right be the positive x direction. We'll have a surface charge that's positive on the left plate, and there'll be a negative surface charge for the right plate, but let's say that they're equal and opposite. There will also be a normal unit vector which points from our negative plate towards point P. Notice that the direction of the normal vector for our positive plate will be positive I, but the direction pointing from our negative plate toward point P will actually be in the negative I direction. So we want to substitute everything in here. For simplicity's sake, I'll let the sigma of the positive plate be represented by sigma, and the sigma of the negative plate can be represented by negative sigma. That'll give us sigma over 2 epsilon naught I hat plus negative sigma over 2 epsilon naught negative I hat. Combining these together, we get that the electric field will be 2 times sigma over 2 epsilon naught I hat, which is simply sigma over epsilon naught I hat. This shows that the electric field inside a capacitor is given by the surface charge on the two plates over epsilon naught.